Hello, welcome to Mechan 2040 Solar Mechanics. I am Globas. In this tutorial, we are going to discuss about transformation equations and the Mohr circle. The tutorial agenda will be like this. First, we will do some simple review of stresses in inclined planes, which we have already discussed in previous tutorials. After doing the review of stresses in inclined planes, we will combine the stresses in inclined planes caused by pure torsion and pure axial load to transformation equations, which is one of the most important concepts in this chapter. Besides, we will try to find the maximum value of transformation equations, which is called the principal plane and principal stress. We are also interested to the maximum shear stress obtained from the transformation equations. Another important thing in this tutorial is to combine all our transformation equations into a Mohr circle. It can give you a very direct impression on what is the relationship between the direct stress and shear stress for an element at different orientation. We also talk about plane strain. Let's do some simple review of stresses in inclined planes. In previous tutorials, we discussed the stresses in inclined planes due to pure axial load and pure torsion. In this case, it is talking about a pure axial load. Under the pure axial load, the direct stress on an inclined plane is given by p cosine squared theta divided by a, while the shear stress on the inclined plane is given by p cosine theta sine theta divided by a. Besides, we also talked about the case of pure torsion. Under pure torsion, the direct stress caused by it is tau sine 2 alpha, while the shear stress is given by tau cosine 2 alpha, where tau is the shear stress induced by the pure torsion. In this chapter, we are going to combine the stresses of inclined planes under axial stress and the pure torsion together to get the transformation equations. In tutorial 1, we discussed the sign convention of shear stresses and direct stresses on a cubical differential stress element. In this tutorial, we will consider the plane stress, that is, all loading, all stresses are lying on the same plane. So here is an example of a plane under plane stresses. So for the stress element inside this plane, the stresses on it is also plane stresses. So we only consider a 2D case of stress, and we try to simplify the problem. Okay, so for the general 3D case, I think it will be discussed in some advanced course. Now let's try to derive the transformation equations by considering a stress element located inside a plane under plane stress. Consider a thin plate stress element. Then, on the four sides of it, there will be 8 stresses, namely 2 pairs of axial stresses in the horizontal and the vertical direction. There are also 4 shear stresses acting on the surface of the stress element. As we discussed in the previous tutorial, the shear stresses on the stress element are of the same magnitude. Therefore, we can simplify the stress element such that all those 4 shear stresses share the same notation, tau xy. Now, if we try to incline this stress element and we create an x1, y1 coordinate system, then after the stress element is being rotated, the stresses on this piece of stress element will still be 2 pairs of direct stress and the 4 shear stresses on the surface. But we will change the notation a little bit because there will be change inside it. For the 2 pairs of direct stress, we name it tau x1 and the tau y1. For the 2 pairs of direct stress, we name it sigma x1 and the sigma y1 respectively. While for the shear stresses inside the stress element, we call it tau x1 y1. Now we will try to consider the force equilibrium by cutting this stress element into such a kind of piece. That is, we try to get a piece of stress element like this. From here, we cut it down. Bear in mind that we're studying solid mechanics, so no matter how I cut the stress element, the stresses inside it will also be in equilibrium. So if we take this piece of stress element, then on the two orthogonal sides, there will be sigma x and sigma y, as well as tau xy, while on the inclined plane, we will have tau x1, y1, and the sigma x1. So it is quite similar to this one. Okay, so we just move them over there. However, it is not really a triangle. We consider this stress element as a wedge. That is, probably the shape would look like this. So it is a kind of wedge-shaped planar element. So for this surface, it has an area of A0. We define this angle to be theta. Then the area of this side will become A0 tangent theta. And consequently, for the area lying on the hypotenuse, it will become A0 secant theta. So it is exactly shown here, but it is shown in 2D form, so I try to sketch the 3D form to help you understand. So still, I emphasize, it is not really just a triangle. It is actually a wedge. It looks like this. You can imagine you have a sandwich, okay? Then this side will be A0, this side will be A0 tangent theta, and this side will become A0 secant theta. Now, although we know all the stresses on this wedge, but we don't know what is the force equilibrium of it. Still, to emphasize, we just know the stresses inside this wedge, but we don't know the force. But we can find the force by using stress times area. So for this side, the area is A0. For this side, the area is A0 tangent theta. For this side, the area is A0 secant theta. For those two orthogonal sides, the stresses on it are sigma x, sigma y, and tau xy respectively. The stress are sigma x1 and tau x1, y1 respectively. Now we try to decompose all those forces into x1 and the y1 directions in this coordinate system. Then we will get the following very complicated expression. So I will leave you to read by yourself. But basically, what is theta? Theta is just this angle. Okay, then you will find sigma y A0 tangent theta, tau xy A0 tangent theta, tau xy A0, and sigma x A0 in x1 and y1 direction, such that we can do some computation with respect to sigma x1 A0 secant theta, as well as tau x1 y1 A0 secant theta. So in x1 and y1 directions, the equations are shown here. Then we try to simplify the system, and we make sigma x1 and the tau x1 y1 to be the subject. Then we can have those two equations. By the system we derived in the previous slide, we rewrite the terms inside this equation by using the trigonometric relationships. Here we have 2 sine theta cosine theta, which equals to sine 2 theta. Also, here it is minus cosine 2 theta. Here it becomes 1/2 of sine 2 theta. So here we just group all of them together. We can do some preparation before we really simplify them by using the trigonometric relationships. Here, from this step to this step, we use tau x1, y1 to be the subject. Then the shear stress on the inclined plane is given by tau x1, y1 equals to tau xy cosine 2 theta minus 1/2 of sigma x minus sigma y times sine 2 theta. Still, for the first equation, it is still not yet settled, but if we consider the first equation, then it looks like this. However, we can rewrite the cosine square theta and the sine square theta in this bracket in this form. After that, what to do is just to expand this bracket and then get the direct stress on the inclined x-plane, which is sigma x1 equals to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 times cosine 2 theta plus tau xy sine 2 theta. So from the previous slide, we have tau x1, y1 and the sigma x1. At the same time, you can also have the direct stress in the y1 direction by simply substituting the theta by theta plus pi divided by 2. After that, you will get the equation of sigma y1. Notice that the first term are still the same, but for the rest of the two terms, they have opposite signs. For sigma x1, you can obtain a positive sign for those two terms, while for sigma y1, you obtain two negative signs. At the same time, if you try to add those two equations together, then you will get this result. That means the sum of the direct stress in x1 and the y1 directions is equal to the sum of the direct stress in x and y directions. Notice that the requirement of this course is to let you apply those two important results. Notice that basically the course requires you to apply those two very important formula instead of expecting you equipped with all the theoretical background about those two formula, because those two equations are very complicated in my opinion. And when I was taking this course, I also feel quite confused. But anyway, those two in general, you can put them on your cheating sheet, so I don't think it would be a big problem. Anyway, try to understand those two equations very well by using the examples in this tutorial, which I will provide you later. Let's have a look of some very special cases of the transformation equations. First special case is the uniaxial stress. Uniaxial stress means that there is no shear stress, and there is the direct stress in only one direction. That means if we say, okay, sigma x is non-zero, then sigma y equals to 0, then those two equations can be greatly simplified. Tau xy equals to 0, sigma y equals to 0. Then what's remaining is minus sigma x times sine theta cosine theta, because what's remaining is just minus sigma x divided by 2. But you know, sine 2 theta equals to 2 sine theta cosine theta. So what's remaining is just minus sigma x sine theta cosine theta. Similarly, for the direct stress in x1 direction, we know there is no shear stress and there is no sigma y. What's left here is just sigma x divided by 2 plus sigma x divided by 2 cosine 2 theta. Well, if you take sigma x divided by 2 out, and in the bracket it will become 1 plus cosine 2 theta. Well, it is just 2 cosine squared theta, right? So it is sigma x divided by 2, 1 plus cosine 2 theta. Well, this one will become 2 cosine squared theta. Okay, but this 2 is vanished by the denominator. Therefore, what's left is just sigma x cosine squared theta. So those two formula are exactly comparable to the conclusion what we have drawn in the previous chapter when we were talking about the stresses on inclined plane. Now let's talk about the case of pure torsion. For pure torsion, we know that there is no direct stress acting on the system. There is only shear stress. So we can kill a lot of terms in those formula. So sigma x and sigma y are both 0, so this is completely 0. So the shear stress of inclined plane is given by tau x1 y1 equals to tau xy cosine 2 theta. Besides, for the direct stress of the inclined plane, we have sigma x and sigma y equals to 0, so the two terms in the front are eliminated. What rests in this formula is just tau xy sine 2 theta. Therefore, the direct stress in the x1 direction is given by tau xy sine 2 theta. Another relatively special case is the biaxial stress. That is, there is no shear stress, and for the direct stress, they are both non-zero. In this case, we can eliminate those two terms in the formula. Therefore, we can obtain the shear stress of inclined plane as well as the direct stress in x1 direction by those two formula, which is obtained by directly removing those two terms. After talking about the transformation equations and the special cases involved, then let's try to introduce the concept of principal plane and the principal stress. Very often we care about the extremum of stress inside the material. For example, the maximum stress, because we care about the impact of stress inside the material, and we have to calculate what is the maximum inside such that we can really choose the correct material that we want. An inclined plane with maximum magnitude of direct stress is said to be a principal plane, and the stress is called principal stress. So the principal plane and the principal stress is basically talking about at what angle of inclination you can obtain the maximum stress inside the stress element. To do this, we are going to find the maximum of the stress with respect to theta. Still, recall that we are talking about angle of inclination. Therefore, we are interested to the variation of stresses with respect to theta, the angle of inclination. That is, we try to model our transformation equation as a function of theta. So as what we have learned before, we know that the transformation equation has a lot of variables like the sigma x, sigma y, as well as tau xy. But here we mainly concentrate on theta, the angle of inclination. To find the principal plane or the principal stress, the first step we need to do is to take the derivative. The objective is to find the maximum, so we will take the derivative with respect to theta. Then the sigma x1, the theta, after differentiating this thing, equals to minus sigma x minus sigma y. We wish to solve when the derivative equals to 0. Then this equation will become this. Solving for this equation, we can have 2 tau xy cosine 2 theta p equals to sigma x minus sigma y sine 2 theta p. Then we have tangent 2 theta p equals to 2 tau xy divided by sigma x minus sigma y. However, instead of writing tangent 2 theta p in this term, we divide by 2 in both numerator and the denominator for some reasons. So I will tell you the reason a little bit later. So eventually you will get tangent 2 theta p equals to tau xy divided by sigma x minus sigma y divided by 2. Then, since we are talking about tangent 2 theta, we can draw this right angle triangle in this way. This angle is 2 theta p. Tangent theta equals to tau xy divided by 1/2 of the difference of the direct stress, sigma x and sigma y. Then, by Pythagoras theorem, we can find R. The reason why we name it to be R will be discussed a little bit later, but at this moment, you just remember, okay, R is a quantity which represents the hypotenuse of this right angle triangle. Next, we want to solve for the stresses. So still recall that we are going to find the principal plane and the principal stress. Therefore, we want to solve for theta and the stresses, okay? However, for tangent 2 theta p, we can decompose it into sine divided by cosine, right? But for sine divided by cosine, there are two forms that you can write. One is that both of them are positive. Another form is that both of them are negative. So note the difference in symbol. Now let's consider the principal stress, which is the direct stress sigma x1 theta. Transformation equation says this. Now let's consider this equation. So the reason why we write tangent 2 theta into sine 2 theta divided by cosine 2 theta, the reason behind is that in the transformation equation we only have sine 2 theta and cosine 2 theta. So by writing tangent 2 theta in this way, we can do the direct substitution into the equation. Anyway, substitute the two groups of possible values cosine 2 theta and the sine 2 theta into the transformation equation. First, we substitute the first system into the transformation equation. Then the first principal stress is given by 1/2 of sigma x plus sigma y plus sigma x minus sigma y divided by 2 times cosine 2 theta, which is sigma x minus sigma y divided by 2r. Then the whole term becomes this thing, okay? It is not the end. Next, we substitute sine 2 theta into the equation, which is tau xy divided by r, and then you times with the tau xy located here. Then this term will become tau xy squared divided by r. We further simplify this expression by grouping those two terms with the same denominator. Then you can have this expression. Finally, we take 4 from this term, okay? We take 4 out such that it can be cancelled with the denominator. Then the thing left in this bracket will be something like this. However, still, what is r? Just now we said r equals to square root of sigma x minus sigma y divided by 2 squared plus tau xy squared, okay? But you can see here there is no square root, so this term will automatically become r squared. And here the r squared is cancelled with r, then this term will become r. Therefore, sigma 1 equals to sigma x plus sigma y divided by 2 plus r. And you know r is just something like this, a square root. So there is another principal stress which is similar. You are going to substitute this system into the transformation equation. Then everything are the same except the symbol become negative. Then we group those two terms behind. Then this will be negative. All the rest of things are still the same. By the similar procedures, you can make the numerator to be 4r squared, cancelled with the denominator 4r. Eventually, you will get minus r behind. Therefore, the second principal stress is given by sigma 2 equals to the average of the rest stresses minus r. Next, we talk about the maximum shear stress. So just now, we talked about the principal stresses and the principal planes, and the method how to find the principal plane as well as the principal stress. So now let's talk about how to find the maximum shear stress. So notice that for principal stresses, it is just talking about the direct stress, but for the maximum shear stress, it is just maximum shear stress. It does not have some name like principal shear stress. No, there is no something like this. There is no something like this, okay? It is just maximum shear stress. Recall the transformation equation of the maximum shear stress. Then we take the derivative of it with respect to theta still, just like what we did for the direct stress. Then you will get d tau d theta equals to minus 2 tau sine 2 theta minus sigma x minus sigma y cosine 2 theta. And we solve it when the derivative equals to 0. Then we have tangent 2 theta s equals to minus cotangent 2 theta p. What does that mean? So after solving the system, you will have minus 2 tau xy sine 2 theta equals to sigma x minus sigma y cosine 2 theta s. Okay, s. So theta s is just representing the maximum shear stress. Okay. Then by rearranging the terms, you can have tangent 2 theta s equals to minus sigma x minus sigma y divided by 2 tau xy. It just equals to minus sigma x minus sigma y divided by 2 over tau xy. Let's compare this result with what we have got just now. Just now, we got tangent 2 theta p equals to tau xy divided by sigma x minus sigma y divided by 2. Now we have tangent 2 theta s equals to minus sigma x minus sigma y divided by 2 divided by tau xy. Immediately, you can find the relationship that tangent 2 theta p equals to minus cotangent 2 theta s. Because you can observe from them, you can get this relationship. Tangent 2 theta p equals to minus cotangent 2 theta s. We can still write in this form. Tangent 2 theta s equals to minus cotangent 2 theta p. By the trigonometric relationship, we know that tangent x equals to minus cotangent x plus minus pi over 2. Therefore, we have 2 theta s equals to 2 theta p plus minus pi over 2. Then theta s equals to theta p plus minus pi over 4. So it is the relationship between the angle of inclination where the maximum shear stress occurs and the principal plane angle of inclination. So we make it clear, theta s is the angle which maximum shear stress occurs, while theta p is the angle which represents the maximum direct stress occurs. And for theta p, it also has another name called principal angle. The plane with such a kind of principal angle is called the principal plane. So this equation just describes the relationship between theta s and theta p. After we get in the relationship between theta s and theta p, then we can find the maximum shear stress. Still, this is theta p, okay? All things are just very similar, except we add pi over 2 after the 2 theta p term, such that we can find the maximum shear stress. Still, remember that cosine x plus pi over 2 equals to minus sine x. Cosine x minus pi over 2 equals to sine x. Then we get cosine x plus minus pi over 2 equals to minus plus sine x. Similarly, sine x plus pi over 2 equals to cosine x. Sine x minus pi over 2 equals to minus cosine x. Then we have sine x plus minus pi over 2 equals to plus minus cosine x. So here it will become minus plus sine 2 theta p. Here it will become plus minus cosine 2 theta p. But luckily there is a negative sign assigned here such that it will become minus plus. So eventually you can write both of the minus plus into the way of plus minus. Okay, then the maximum shear stress is given by tau x1 y1 theta s equals to plus minus tau xy sine 2 theta p plus minus sigma x minus sigma y divided by 2 cosine 2 theta p. So still we keep the plus minus sign here. We do the simplification by substituting sine 2 theta p and cosine 2 theta p into the expression. Also, by the similar procedure, we make r to be the common denominator such that we can make the numerator like this, and immediately you can find it is just r squared. Finally, you will get the result, which is plus minus r. Therefore, the maximum shear stress of a stress element is given by r. However, another important observation is that when you have a log of sigma 1 and sigma 2, you can find that both of the sigma x plus sigma y divided by 2 terms are the same. Both of them are the same, okay? But the difference is that the r is plus minus, okay? For sigma 2, it is negative. For sigma 1, it is positive. Therefore, we know that sigma 1 minus sigma 2 equals to 2r. Then sigma 1 minus sigma 2 divided by 2 equals to r. So the maximum shear stress equals to the difference of the two principal stresses divided by 2. After talking about principal stresses and principal planes as well as the transformation equations, let's combine all what we have learned into a new concept, which is called Mohr circle. Here are the two transformation equations we get previously. For the shear stress transformation equation, we call it number 1. For the direct stress transformation equation, we call it number 2. And we do a little bit modification on the transformation equation of the direct stress. That is, we put this term on the left hand side. So originally, it is something like sigma x1 equals to sigma x plus sigma y divided by 2, and plus sigma x minus sigma y divided by 2 cosine 2 theta plus tau xy sine 2 theta. Okay, so we just put this term to the left hand side to get number 2. Now what we have to do is that we square both of the equations and add them together. Then for equation 1, you will get tau x1 y1 squared equals to tau xy squared. Tau xy cosine 2 theta sine 2 theta sigma x minus sigma y plus sigma x minus sigma y divided by 2 squared sine squared 2 theta. Okay, this is 1 squared. For 2, equation 2 squared, it will become sigma x1 minus sigma x plus sigma y divided by 2 squared equals to sigma x minus sigma y divided by 2 squared cosine squared 2 theta plus tau xy cosine 2 theta sine 2 theta sigma x minus sigma y plus tau xy squared sine squared 2 theta. Then for the left hand side, it is combined to be something like this. So sorry that here it should be cosine 2 theta squared. Okay, so I missed this term. So for tau xy squared, we first take out tau xy squared, and then we combine those two terms together. Then we have something like this. And obviously you can observe that this term automatically becomes 1. For sigma x minus sigma y squared divided by 2, this term, you can also group them together. Here is sine squared 2 theta, and here is cosine squared 2 theta. Then those two added together equals to 1. At the same time, we observe those two terms are exactly the same except the symbol. That is, those two terms are placed here and being vanished to be 0. Then, after we do a lot of simplification, you can have tau x1 y1 squared plus sigma x1 minus sigma x plus sigma y divided by 2 squared equals to tau xy squared plus sigma x minus sigma y divided by 2 squared. So here, this stuff is just r squared, okay? At the same time, we define the average direct stress to be sigma 1 plus sigma 2 divided by 2, which is the average of the principal stresses. But just now, we also discussed that sigma x plus sigma y equals to sigma 1 plus sigma 2. So here we discussed that for any angle of inclination, the sum of the direct stresses are always the same. The same also applies to the principal stresses. Then this term will become sigma average. Then what to left here is this equation. Sigma x1 minus sigma average squared plus tau x1 y1 squared equals to r squared. Notice that it is a constant, okay? R squared is also a constant. Notice that here sigma average is a constant, r is also a constant. The variables inside the circle are sigma x1 and the tau x1 y1. Then you can observe that it is an equation of circle. The Mohr circle has a center located at sigma average 0 with the radius r. By using your knowledge you learned in the secondary school about the equation of the circles. And recall that r equals to this stuff. In summary, when you want to draw a Mohr circle, bear in mind with the center and the radius. For a Mohr circle, there are two ways that we can draw it. One is the ordinary coordinate system, something like sigma x1 and tau x1 y1. However, we seldom use this in the solid mechanics course. It is because 2 theta is positive in counterclockwise direction, as what we defined at the beginning. It is exactly the direction we adopted when we deriving the transformation equation. So the reason why we don't adopt this is that if we adopt Mohr circle like this, then the direction of 2 theta will be like this, which is not what we want. What we want is the Mohr circle like this, tau x1 y1 and the sigma x1. Then the Mohr circle constructed in this coordinate system will have 2 theta positive in this direction. Now let's do a past homework problem, but I modified it to make it more complicated and integrate with your knowledge learned in transformation equations as well as the Mohr circle. The surface of an airplane wing is subject to the plane stress with normal stresses sigma x and sigma y as well as the tau xy. So here we know what is sigma x. At a counterclockwise angle, theta equals to 32 degrees from the x-axis. The normal stress is 37 milliPascal in tension. At the angle of theta equals to 48 degrees, the normal stress is 12 milliPascal in compression. It is given that sigma x equals to 110 milliPascal tension. We are going to find sigma y and the tau xy, as well as the principal stresses and maximum shear stresses. Besides, I want to construct the Mohr circle for the stress element and find the angle of inclination where the principal stress are occurred. You're also going to sketch the stress element. At the same time, you are going to verify there is no shear stress acting on the element by using the transformation equation when the principal stresses are occurred. Then, find the angle of inclination where the maximum shear stress is occurred by using Mohr circle. Sketch the stress element in this inclination. Besides, you are also going to show by using transformation equation that the shear stresses reach the maximum and the direct stress sigma x1 and sigma y1 are equal for element in part E. So there are a lot of parts, so let's try to solve them one by one. For first problem, you are going to find sigma y and tau xy, and it is given sigma x1 in different angle of inclinations. Therefore, by using the transformation equations, we can write the following system. First, we put the sigma x1 on the left hand side. Then, since we know sigma x equals to 110 milliPascal, we also know theta, which is 32 degrees, and 48 degrees for the next case. So let's have a look of this transformation equation. For this transformation equation, it can be rewritten in this form, which is sigma x cosine squared theta plus sigma y sine squared theta plus tau sine 2 theta, where tau is just tau xy. Okay. Then we know that sigma x1 is given, theta is given, sigma x is also given. So now the variables left in this problem are just sigma y and the tau. In other words, if we can write two equations, then we can solve for sigma y and the tau immediately. In this problem, it gives you two groups of data for your calculation. That means you're going to use two equations to solve for tau and the sigma y. Firstly, substitute all what you know into the equation. At angle 32 degrees, sigma x1 equals to 37 and the theta equals to 32. We also know what is sigma x. Then you can write this equation with unknowns sigma y and tau. Similarly, for the 48 degree inclined case, sigma x1 equals to minus 12, sigma x is known, angle is 48 times 2. Okay, then in this equation, the unknowns are just sigma y and the tau. With those information, you can rewrite the system to solve for tau and sigma y. It is about a lot of numerical operation works, but I think you can handle it. The answers are sigma y equals to minus 60.67 milliPascal, while the shear stress is given by minus 27.9 milliPascals. Next, you are going to find the principal stress and maximum shear stress on this element. Now you have already got tau xy as well as sigma y. Okay, so what you do is just to substitute everything into it. Then you can find the principal stresses. The principal stresses are 114.44 milliPascal and minus 65.12 milliPascal. At the same time, you can also find the maximum shear stress, which is given by R, but you know R is just the difference between the principal stresses divided by 2. Then the maximum shear stress is given by 89.78 milliPascals. Next, by using the results in the previous slides, you are going to construct the Mohr circle for the stress element, as well as find the angle of inclination where the principal stresses are occurred. You're also going to sketch the stress element at this inclination. So as we discussed previously, the equation for Mohr circle is given by sigma x1 minus sigma average squared plus tau xy1 squared equals to r squared. To do this, first we find what is sigma the average direct stress. Well, it is easy to find. You know what is sigma x, you know what is sigma y. Then, by using sigma x plus sigma y divided by 2, you can find the average direct stress is given by 24.66 milliPascal. Also, by using the equation of R, the radius of the Mohr circle is found to be 89.78 milliPascals. In the previous parts, since we get at theta equals to 0, we know that sigma x1 equals to 110 million pascals, and consequently we used our transformation equation to find that the shear stress is given by minus 27.9 million pascals. So by using this Mohr circle, we can also verify that the shear stress we found in previous part is correct. First, suppose we don't know what is tau x1 y1, that is, we don't know what is it, okay? Then we locate a point on the Mohr circle where it represents that sigma equals to 110 million pascals. So on this Mohr circle, the first principal stress is given by 114.4, while the second principal stress is given by minus 65.1. The reason is that sigma 1 equals to sigma average plus r, while sigma 2 equals to sigma average minus r. Then you can locate the center as well as the radius of the Mohr circle, and consequently you can find the principal stresses on the horizontal axis, sigma x1. By using our condition, sigma x equals to 110 million pascal, we can locate the point at here. However, you may wonder, okay, for sigma x1 equals to 110 million pascal, there is another possible point which is lying at here. Then why we can confirm, okay, it is located here instead of located here? The reason is that apart from considering the 110 million pascal direct stress, we also consider the two given conditions, which is at 32 degrees, the direct stress is given by 37 million pascal, while at 48 degrees, the direct stress is negative 12. So let's consider those two cases to see which one is correct. So for this case, if we consider theta equals to 48 degrees, then supposed by what the condition is given, sigma x1 equals to minus 12 million pascal. Let's try to rotate this line by 96 degrees. Then significantly, it will lie in some region like this. Okay, and this point represents that, okay, the sigma x1 is slightly negative. However, if we are talking about this point, if we say okay, theta is 0 here, then by rotating 96 degrees, you can see, okay, it is actually not making sense as the sigma x1 is not negative 12. You can also verify by using the data of theta equals to 32 degrees. So still being in mind that for the angle here, it represents 2 theta instead of theta. So for theta equals to 48 degrees, we rotate by 96 degrees of this line, okay? And similarly, for theta equals to 32 degrees, we rotate this line by 64 degrees. Also, at this point, we know that direct stress is 110 million pascal. Then we can compute tau xy directly by using the geometry of the circle. So we substitute sigma x into this equation. At the same time, we know what is the radius of the circle. Therefore, we can compute tau x1 y1 by using the formula. The result will be negative 27.9, which agrees with our results previously. So our result after solving this system is given by negative 27.9 million pascal. So it is exactly the same to what we found from the Mohr circle. Notice that although this point is lying above the horizontal axis, but still recall that we adopt the vertical axis to be reversed. That is, for a point lying above the horizontal axis, it represents a negative shear stress. Therefore, we can find alpha, which is the angle between this line as well as the horizontal axis. Alpha equals to arc cosine 110 million pascal minus 24.66, which is the average direct stress, divided by radius. The result is 18.1 degrees. Consequently, we can find the principal stresses. So recall that principal stresses is the maxima and the minima of direct stress. The principal stresses are located here and here. Here we call it sigma 1, while here we call it sigma 2. For sigma 2, it has a principal angle of theta p2. Here it represents theta equals to 0. Then 2 theta p2 represents this angle from theta equals to 0 to the second principal stress, which the value is smaller. 2 theta p2 is around 162 degrees, then theta p2 equals to 80.9 degrees. Similarly, for sigma 1, we consider this angle. This angle represents 2 theta p1, but it is just adding 180 degrees from 2 theta p2. Therefore, theta p1 equals to 80.9 degrees plus 90 degrees equals to 170.9 degrees. After we getting theta p2 and theta p1, we can construct the sketch of this stress element. Rotating this stress element counterclockwise by an angle of 80.9 degrees means that those two surfaces represent 80.9 degrees, while those two surfaces represents 170.9 degrees. So to do this, first, for 80.9 degrees surfaces, we know that the principal stresses is given by minus 65.1, which means the stresses on 80.9 degree surfaces are 65.1 milliampascal in compression. At the same time, for the 170.9 degree surface, the principal stress is given by 114.4 milliampascal in tension. Next, we try to verify that there is no shear stress acting on the element in C by using the transformation equation. That is, we are going to prove that for the principal stresses, that is, the maximum direct stress occurs, there is no shear stress acting on the stress element. As what we predicted in the previous slide, there was no shear stress. To do this, we just substitute those two angles into the transformation equations, as well as what we got for tau xy, sigma x and sigma y. We substitute everything inside this transformation equation, and eventually we get 0. How about the angle of inclination where the maximum shear stress is occurred? Try by using the Mohr circle. So for the maximum shear stress, observe that this Mohr circle is symmetrical about sigma x1 axis. To do this, we draw a vertical line which passes through the center of the Mohr circle. It is significant that those 2 points represents the maximum and the minimum shear stresses, but actually, the shear stresses are just equal in magnitude. So on this vertical line, you can obtain the maximum shear stress. To do this, first, we know that 2 theta s equals to 90 degrees minus alpha, then theta s equals to 35.95 degrees, and similarly, theta s2 equals to 35.95 degrees plus 90 degrees, but actually there is nothing that we can do with it because this surface is 35.95, but adding 90 degrees is automatically this surface, so actually there is no much thing we can do because we suppose the stress element is a square. Then we can also sketch the stress element at this inclination. We found that the direct stress acting on the stress element in x1 and y1 directions are the same, which is 24.7 milliampascals. We also know that the shear stress acting on the stress element is given by 89.8. Then we can sketch the stress element like this. So notice that all the units in the sketch is milliampascal. Finally, you are going to use the transformation equation to show that all your conclusions in the previous part is correct. So it asks you to show that the shear stress attains the maximum, as well as you are going to show that the direct stress on x1 and y1 directions are the same. To do this, we substitute theta s1 into the transformation equations of the direct stresses. You will get the same answer, which is 24.66 milliampascals. You repeat the above procedures by using theta s2 substitute it into the transformation equations, you can get the same answers. To show that the shear stress reached the maximum, you are going to use the transformation equation in this way. First, you have your transformation equation, then differentiate your transformation equation with respect to theta. You will get this expression. Then you are going to substitute the value of theta s1 and theta s2 into d tau d theta. Then, if the result is 0, then you are successfully verified that what you have found is the maximum. Let's go through another more theoretical example to help you understand the Mohr circle even better. By using the Mohr circle, show with explanation by graphical method. So you are going to look at the Mohr circle to do some explanation. That unless maximum shear stress occurs, it is impossible that sigma x1 equals to sigma y1. Sigma x1 and sigma y1 are equal in magnitude for any angle of inclination if and only if sigma average equals to 0. Shear stress is equal in magnitude at any angle of inclinations. Theta s equals to theta p plus minus pi divided by 4. It is impossible that tau x1 y1 equals to sigma x1 if the magnitude of the average direct stress is larger than square root 2 of r. Part A asks you to show that unless maximum shear stress occurs, it is impossible that sigma x1 equals to sigma y1. So as you can see, very often we treat a stress element inclined at an angle of inclination of theta to be something like a line passing through the center touching the arc at 2 points. So it is 2 theta, okay? Then this is theta surface and this is theta plus 90 degrees. Here is theta. Then by treating the stress element in this way in Mohr circle, then you will find that at this surface the direct stress is something like this, while at this surface the direct stress is something like this. They are different. They are always different until you draw a very perfect vertical line passing through the center of the Mohr circle. Then you will see on every surface of the stress element they will have the same direct stress, which is just the average direct stress. Next, you are going to show that sigma x1 and sigma y1 are equal in magnitude for any angle of inclination if and only if the average direct stress is 0. To do this, first we have a look of the circle. For any Mohr circle, we know that the principal stresses sigma 1 and sigma 2 equals to average plus minus r. First, we try to make the principal stresses equal, so we set sigma average equals to 0 so that the principal stresses has the same magnitude. Then we can draw a Mohr circle as shown here. For this Mohr circle, as long as it has equal magnitude of principal stresses, the direct stress at any angle of inclination can be found in this way, and then you can find that they are automatically the same. Therefore, we draw a conclusion that sigma x1 and sigma y1 are equal in magnitude for any angle of inclinations if and only if the average lies at the origin. Shear stress is equal in magnitude at any angle of inclinations. Well, you can have a look of the proof without words. So actually, Mohr circle is symmetrical about sigma x1 axis. So no matter how you rotate your stress element, as long as you draw a straight line passing through the center, the line will cut with the circle at 2 points with positive and negative tau x1 y1. Although shear stresses has opposite signs, but they have the same magnitude. You are going to show that the angle of inclination where the maximum shear stress occur equals to the principal angles theta p plus minus pi divided by 4. So to do this, first let's draw a horizontal and a vertical line over the Mohr circle. For this vertical line, it represents the occurrence of maximum shear stress, while for the horizontal line, it represents the occurrence of principal stresses. The angle between those two lines is given by delta 2 theta, That is 2 theta s equals to 2 theta p plus minus delta 2 theta, while delta 2 theta equals to pi over 2. That means theta s equals to theta p plus minus pi over 4. Because no matter how you rotate this line, counterclockwise or clockwise, you are able to draw those two lines. It is impossible that the shear stress equals to the direct stress if the average direct stress is greater than square root 2 of r. To do this, actually I've wrote a lot of explanations here, but actually you can try to understand this by using our graph. Firstly, let's draw tau x1 y1 equals to sigma x1, this line, this strict line, okay? In order to make tau x1 y1 equals to sigma x1, we wish this line, the green line, can cut with the red circle, which is the Mohr circle we draw. We know that if a circle is cutting a line, then the radius is perpendicular to the tangent. Then let's magnify this triangle. For this triangle, sigma average is here, r is here, and we have this and this 90 degrees line here. At the same time, for this straight line, it has an angle of 45 degrees. So this angle is 45 degrees. That means this angle is 45 degrees as well. Then it is a right-angled isosceles triangle. That is sigma average equals to square root 2r. However, if sigma average is too large, that it is larger than r, then it is no longer possible for this circle to cut with the straight line. Similar case for sigma average less than 0. Finally, let's talk a little bit about plane strain. So those equations are for reference. Transformation equations for plane strain is rather similar to that of stress, but the derivation is much more complicated. So the following are just some equations for the plane strain. Also, you can find the principal strains shown here. Finally, let's do some summary. We introduced 3 transformation equations, which is here, as well as the relationship between the direct stresses. The direct stresses are conserved. Also, we talked about the principal stresses, sigma 1 and sigma 2. Also, we observed that sigma 1 plus sigma 2 equals to sigma x plus sigma y, which consequently equals to sigma x1 plus sigma y1. Also, the method of finding the principal angles is given by tangent 2 theta p equals to tau xy divided by sigma x minus sigma y divided by 2. We also discussed about maximum shear stress, which is equal to plus minus r. It is also 1/2 of the difference between the two principal stresses. The relationship between theta s and theta p is also discussed. For Mohr circle, we used our concepts in transformation equation. We try to combine all those equations together to get a Mohr circle, which is look like this. The radius is given by r, where r is this bunch of stuff. Also, notice that for drawing Mohr circle, we adopt this coordinate system. We are not going to adopt this coordinate system. Instead, we adopt this coordinate system, sigma x1 and the tau x1, y1. To construct a Mohr circle, first locate the point where theta equals to 0, as well as find the stresses for element inclined at different angle theta by rotating 2 theta in Mohr circle. So bear in mind that angles in the Mohr circle is 2 theta instead of theta. There are also some special properties of Mohr circle described in the previous exercise 6.2. We also simply introduced you the plane strain equations. So you can observe they are very similar to the transformation equations of the direct stress and the shear stress. However, there is also some difference that you need to bear in mind with. We also talk about principal strains. For this tutorial, there are 2 exercise problems. Each of them carry 40 marks. The following table are for your reference and self-evaluation. Again, a disclaimer is that the following table just gives you an estimate of your grade, and your true grade received after your final exam depends on your real performance during the examination, as well as your understanding to your course content. Finally, thank you for watching this tutorial, and see you in the next week.